Welcome to Talk Tensors. On this episode, you are covering a trending or viral technology in AI, machine learning, or computer science.
Yeah, and it is a massive one today.
It really is. Usually when we think about a massive industry-changing technology, I always imagine stepping into like a 3 Michelin star restaurant.
Oh, I like that analogy.
Right, like you sit down at the table, the waiter brings out this incredible, mind-blowing dish, and you can taste all these complex flavors. It's an entire experience.
Absolutely.
But the kitchen doors, they are locked tight. You have absolutely no idea what ingredients went into it or what temperature the oven was set to.
Or what techniques the chefs even used, yeah.
Exactly. You just get to consume the final product and marvel at it. You can't go home and cook it yourself.
And I mean, the proprietary nature of the tech industry really forces that dynamic. You can enjoy the meal, maybe guess a few of the spices, but the actual mechanics of the creation are just hidden behind a wall of corporate secrecy.
Right. And for the last couple of years, that is exactly what the artificial intelligence industry has felt like.
Completely.
But today, our mission for this deep dive is to essentially kick those kitchen doors wide open.
Yes. Funny.
We were looking at a really groundbreaking development called Tulu 3.
It's a game changer.
It is. So this is a family of open-weight, large language models, and they're available in 8 billion, 70 billion, and this massive 405 billion parameter size.
It's just huge.
Right. But we aren't just looking at the models themselves. Like the real story here is that we are analyzing the fully open recipe used to build them.
And I think the distinction between, open weights and an open recipe is absolutely crucial for you, the listener, to grasp right out of the gate.
Yeah, break that down for us.
So for the last year or so, the entire AI industry has sort of operated on this largely unspoken truth.
Which is?
The secret to creating frontier models, like the ones that feel truly intelligent, coherent, useful, it isn't just the initial training phase. It's actually this phase called post-training.
Post-training.
Right. Yeah. Which refers to the meticulous steps taken after a base model has essentially, read the entire internet. Post-training is the actual secret sauce.
But the closed AI labs, they treat these post-training recipes like highly classified state secrets.
Oh, completely. Yeah. They'll give you the dish, right. They'll even let you download the weights of some models sometimes.
Yeah,
but they will never, ever give you the step-by-step recipe.
Until now.
Yeah.
Because Tulu 3 basically rips the lid off this black box.
It really does.
It provides the data, the code, the evaluation framework, and the exact sequential training pipeline that allows an open model to rival, and in some cases even beat, proprietary giants.
Giants like GPT-4 Mini and Claude 3.5 Haiku. It's wild.
It is wild. Definitely. So you, the listener, are getting a VIP behind-the-scenes tour of the exact mechanics used by top-tier AI labs. We are finally demystifying the magic here.
And it represents a massive paradigm shift in how the scientific community approaches open research.
I agree.
But to fully appreciate why this matters right now, we kind of have to look at what we call the post-training bottleneck.
Okay, yeah. Let's unpack that.
We need to understand the exact technical reasons why the OpenAI community had hit a wall, and why post-training became the ultimate battleground for artificial intelligence.
Right. So what exactly makes the Tulu 3 approach so different from earlier open models?
Well, to start, we have to ground ourselves in what a base model actually is.
Because Tulu 3 is built on top of the Lama 3.1 architecture, right?
Exactly. Now, a base model is incredibly powerful, but it is super raw. Under the hood, it is essentially the world's most advanced autocomplete engine.
Just predicting the next word.
That's its sole mathematical objective. Predicting the next token, which is usually a word or a piece of a word in a sequence.
And it does this based on just the vast, unfiltered expanse of the internet it consumed during its initial training run.
Right. It has ingested Wikipedia, it has processed Reddit threads, it has scanned complex scientific journals.
And it has absorbed absolute unfiltered nonsense too.
Oh, tons of nonsense. And because of this, its behavior is highly unpredictable.
Like if you prompt a raw base model with the phrase, how to bake a cake,
it might respond with how to bake a pie simply because it calculates that a list of baking questions is statistically likely to follow your prompt.
It has no concept of you wanting it to act as a helpful assistant.
None. It doesn't know you're asking it a question.
I always visualize it like this training a base model is like taking a human being and forcing them to memorize the entire dictionary and every encyclopedia in existence.
That is a lot of reading.
Right. They know literally everything. Their factual recall is unparalleled, but they have absolutely zero social skills.
They don't know how to hold a conversation.
Exactly. Post-training, then, is sending them to a strict corporate boot camp.
I love that analogy.
It's where they learn how to sit at a desk, how to interpret a boss's complex and, nuanced instructions, and how to actually do a useful job without just rambling incoherently about unrelated facts.
And that boot camp analogy tracks perfectly with the historical struggles of open source AI.
How so?
Well, historically, the open source community's version of that boot camp was severely underfunded and technically lacking.
Like a really cheap seminar in a hotel lobby.
Exactly. Open source post-training relied on cheap, relatively simple pipelines. Researchers would use basic instruction tuning.
Just the bare minimum.
Yeah, maybe scrape some interactions from older, less capable models, run a quick training loop, and call it a day.
And the consequence of that approach was pretty severe, wasn't it?
Oh, drastically. They fell way behind the proprietary models on complex, multi-step tasks.
Like math and coding.
Right. They couldn't perform advanced mathematical reasoning, they couldn't write complex, bug-free Python code, and they uniquely struggled with precise instruction following.
Let's actually define what we mean by instruction following, because it sounds simple, but it's computationally brutal.
It is incredibly hard.
It's like when you tell a model to write an essay about the French Revolution, but you strictly forbid it from using the word the, and you demand it outputs exactly 3 paragraphs in a JSON format.
Which is an incredibly hostile environment for an autocomplete engine.
Right, because it just wants to predict the next most likely word.
Exactly. A base model naturally wants to use the word the because it is statistically one of the most common words in the English language.
It's fighting its own instincts.
Overriding that deep-seated statistical urge requires an incredibly forceful and precise post-training regimen.
And that brings us to what's so fascinating here.
The sheer level of transparency and scientific rigor.
Yes. The Tulu 3 developers applied so much rigor to solve this exact problem.
Because Tulu 3 isn't just an artifact you download, right? It is a meticulously engineered 4-stage pipeline.
4 stages.
Yeah, and the developers systematically evaluated every single step of this pipeline.
They didn't just guess.
No, they created separate development test sets and entirely unseen test sets to guarantee the model wasn't just memorizing the answers to the test.
They are publishing the exact blueprint for how a frontier model is forged in the fires of modern compute.
It's unprecedented.
So we have this raw base model, our encyclopedia reader, with no social skills.
Right.
To build our perfectly behaved corporate worker, we logically first need to show them examples of flawless work.
We have to show them the template.
And that brings us to the foundation of the pipeline, stage 1 and 2 data curation, and supervised fine-tuning, or SFT.
Supervised fine-tuning operates exactly how the name implies.
Tell us how it works.
So you provide the neural network with a prompt, that's the input, and a perfectly crafted human-level or superhuman-level completion. That's the target output.
You're showing it the exact formatting, tone, and quality of the response you expect it to generate.
Exactly. The network processes the prompt, attempts to guess the answer, compares its guess to your perfect completion, and calculates a loss based on how far off it was.
The loss.
Yeah, and then it adjusts its internal weights to make that specific mistake slightly less likely next time.
And doing that once doesn't really matter.
Right. No, doing it once is meaningless. But doing it millions of times across a diverse set of examples, that slowly sculpts the model's behavior.
So the Tulu 3 process starts by curating these millions of prompts from public data sets.
Right, but they quickly realized that public data has a pretty low ceiling.
Why is that?
Well, they knew that relying solely on what's freely available on the internet lacks the rigorous depth required for specific, highly complex domains.
Because the internet is a mess.
Precisely. The issue with public data is a matter of density and formatting. Nobody is organically posting perfectly formatted, step-by-step grade school math reasoning on forums.
Definitely not.
And nobody is uploading flawless Python debugging scripts structured in the exact conversational cadence the AI needs to learn from.
Like if you train an AI just on Stack Overflow.
Oh, that's a classic example.
Right. It might learn to answer a coding question by just saying, this is a duplicate question, thread locked.
Because that's what it statistically sees the most. It's hilarious, but it's a very real problem.
So how do they get around that?
To circumvent the messy nature of public data, the researchers turned to synthetic data generation.
Using AI to train AI.
Yes, they generated data specifically targeting the base model's inherent weaknesses. They utilized other already advanced models to act as teachers.
So the teacher models generate the perfect textbook for the student model.
Exactly, prompting them to create high-quality, persona-driven synthetic instructions and perfect solutions.
But generating the data is only half the battle, right?
Not even half. Here is where the rigorous engineering comes in. They aggressively decontaminated this data.
Decontamination. I mean, when I read that word in the paper, it sounded like we were operating in a level 4 biohazard lab.
It's treated almost that seriously.
What does decontamination actually mean in the context of feeding text into an AI training pipeline?
Well, if we connect this to the bigger picture, evaluation is the absolute bedrock of AI research. You prove a model is smart by testing it on standardized benchmarks.
Things like GSM 8K for math word problems.
Or human evil for coding tasks, exactly. Now, if the questions from those exact tests, or even close variations of them, accidentally end up in your training data,
Oh, I see.
the entire evaluation is compromised. Your model will look like an absolute genius on the test, scoring perfectly.
But when a user asks it a novel question in the real world, it will fail miserably.
Right. It's the equivalent of a professor accidentally leaving the answer key to the final exam on the projector during a lecture.
The students who saw it haven't actually learned calculus.
No, they've just memorized that the answer to question 4 is 42.
The industry term for this is data leakage, right?
Yes, and it is rampant in poorly constructed open source models. So decontamination is this meticulous, computationally heavy process of scrubbing the training data to ensure no test questions leak into the SFT datasets.
How do you actually do that, though? I mean, you have terabytes of training data and thousands of test questions. You can't just have an intern read through it all and look for matches.
No, you'd need an army of interns. They utilize automated pipelines built around n-gram comparisons.
An n-gram. Let's define that.
An n-gram is simply a contiguous sequence of words. A 1 gram is a single word. A 5 gram is a sequence of 5 words.
Okay, simple enough.
So the decontamination scripts extract long n-grams, perhaps sequences of 10 or 13 words, from the evaluation benchmarks.
And then
They scan the entirety of the millions of SFT training documents. If they find an overlapping n-gram sequence, they flag that training document and completely remove it from the pipeline.
Wow. So if a test question says, like, calculate the trajectory of a train leaving Chicago traveling at an A to go, and that exact string of words appears anywhere in the training data.
That piece of training data is deleted.
Did it entirely. They don't try to edit the sentence.
Delete it entirely. They don't risk trying to edit it. They just excise it.
That is ruthless.
It is, but this draconian approach ensures that when Tulu 3 eventually scores highly on a math benchmark, it's actually performing the cognitive task of mathematics.
Not merely regurgitating a memorized string of characters it saw during SFT.
Exactly.
Okay, so I understand the hygiene aspect. They have all this high-quality, heavily decontaminated data, public conversational data, synthetic math data, synthetic coding data.
Right.
But here is my pushback on this entire stage.
Let's hear it.
If they are mostly using the same public data sets that everyone else has access to, and some synthetic data generated by models that other researchers can also access, why is Tulu 3's performance so significantly better? Isn't this just the exact same ingredients mixed in a slightly different bowl?
That is the core puzzle of modern AI development.
Because everyone in the open source community has access to this raw material, right?
They do. But the secret isn't just possessing the ingredients. It is the exhaustive scientific methodology applied to the exact proportions of the mix, combined with the underlying infrastructure used to process it.
So they didn't just dump it all in.
No, the developers didn't just dump millions of SFT examples into a folder, hit the train button, and hope for the best. They engaged in an incredibly rigorous, methodical process of data mixing.
They treated it like a highly controlled chemistry experiment, not a smoothie blender.
A highly controlled chemistry experiment is the perfect way to phrase it. They established a methodology revolving around what they called upper bound ablation studies.
Let's break down what that means, upper bound ablations.
So to figure out exactly how much math data to include, they didn't guess. They took a raw base model and trained it only on the math dataset. Nothing else.
Creating a highly specialized, hyper-focused math model.
Yes, because if a neural network is only dedicating its billions of parameters to learning math, it's going to hit the absolute ceiling of performance for that specific architecture on mathematical reasoning tasks.
Right, that specialized model establishes the upper bound.
It shows the researchers the maximum possible math score that specific Lama architecture can achieve.
However, there's a trade-off, isn't there?
A massive one. As a consequence of this hyper-specialization, that model suffers from what we call catastrophic forgetting.
Catastrophic forgetting.
Yeah, it becomes brilliant at math, but it entirely forgets how to have a normal conversation, or how to summarize an article, or how to translate languages.
It's like the stereotypical absent-minded professor can solve the Riemann hypothesis, but can't figure out how to order a coffee.
Exactly. So now the researchers have a measurable target. They know the absolute ceiling.
And what do they do with that target?
Next, they take a fresh generalist model and meticulously tweak the comprehensive data mixture.
They start running experiments.
Right. They run a training loop with, say, 10% math data, 50% conversational data, and 40% coding data. They measure the performance.
Then they run another loop with 15% math data.
Yes. They adjust these ratios continuously, slowly pushing the generalist model's math performance closer and closer to that specialized upper bound.
And the goal is to get as close to that upper bound as possible without triggering catastrophic forgetting in the other domains.
You're finding the exact mathematical tension point where the model is great at everything but terrible at nothing.
It requires hundreds of expensive, time-consuming experiments, I imagine.
Hundreds. But the data mixture is only one half of your pushback. The other half involves the actual code infrastructure calculating the learning updates.
Okay, the infrastructure.
And this is where a staggering number of open source projects fail silently without the researchers ever realizing why their models aren't performing well.
What happened?
The Tulu 3 developers uncovered a widespread, insidious bug in standard open source training frameworks. It's known as the batch aggregation bug.
Wait, an actual software bug? Like a literal error in the open source code that everyone was just ignoring or unaware of?
Not ignoring, but unaware of the deep mathematical nuance of how it was affecting loss calculation at massive scale.
Break this bug down for us.
To understand this bug, we have to look at how GPUs actually process text. GPUs don't read words one by one. They perform massive parallel matrix multiplications.
Right.
To do this efficiently, they process data in batches.
So instead of feeding the model one sentence, you feed it, say, 32 sentences all at exactly the same time.
Yes. But here's the physical constraint. The matrices must be perfectly uniform in size. Every sequence in a batch must be the exact same length.
But human language isn't uniform. In a batch of 32 sequences, one prompt might be 10 tokens long, another might be 50, another might be 100.
Right. So how do you make a 10-token sentence and a 100-token sentence fit into the same rigid rectangular GPU matrix?
You pad it.
Exactly. You use something called padding tokens. You take the longest sequence in the batch, let's say it's 100 tokens, and you pad all the shorter sequences with meaningless empty tokens until they also reach a length of 100.
So that 10-token sentence gets 90 blank padding tokens attached to the end of it.
Yes, and the matrix math now works perfectly.
Okay, that makes sense from a hardware perspective. Where does the bug come in?
The bug occurs during the calculation of the loss.
The mathematical signal that tells the network how wrong it was.
Exactly. When you calculate the loss for a batch, you have to average the individual losses of all the tokens.
Right.
Well, the standard open source frameworks were improperly averaging the loss across all the tokens in the matrix.
Including the meaningless padding tokens.
Including the padding token.
Oh, I see the problem. If you have a sequence with 10 actual words and 90 blank padding tokens, and you average the learning signal across all 100 tokens,
the signal from the actual words gets massively diluted by the blank space.
it gets completely washed out.
Washed out entirely. And this problem compounds exponentially when you are using gradient accumulation across distributed training setups with hundreds of GPUs.
The models were essentially spending a significant portion of their compute learning from empty space.
Which resulted in a weak, muddy learning signal.
Wow.
The Tulu 3 team identified this mathematical misalignment and rewrote the loss calculation to strictly ignore padding tokens when averaging.
So they ensured the model was receiving a pure, highly concentrated learning signal derived exclusively from the actual data.
It seems like a minor, almost pedantic engineering detail, just tweaking the denominator in an averaging function.
But fixing this specific bug across billions of training tokens massively boosted the final performance of the model.
Massively.
It tells me that we in the tech world can obsess over neural network architectures and attention heads and parameter counts all day long.
But flawless engineering infrastructure and meticulous data hygiene are just as important, if not more so.
You can have the most beautiful blueprint for a skyscraper in the world, but if your construction workers are using a broken tape measure, the building is going to collapse.
That is the harsh reality of scaling these models. The devil is entirely in the infrastructure details.
All right, so we've completed stage 1 and 2 of the pipeline. We rigorously curated the data, we decontaminated it, we fixed the underlying math bugs, and we mixed the data sets until our corporate worker knows exactly how to answer a prompt.
Right.
But knowing how to answer isn't the same as knowing what a good answer looks like versus a great one.
That's a crucial distinction.
And this moves us to stage 3, preference tuning.
Supervised fine-tuning is fantastic at teaching the model the format, the syntax, and the basic factual grounding. But human language is inherently subjective.
Very subjective.
If you ask an AI to summarize this article, there are mathematically thousands of valid, factually correct ways to do it.
Preference tuning is the mechanism we use to align the model's vast array of possible outputs with actual human values.
Values like helpfulness, harmlessness, clarity, and tone.
And traditionally, for the last few years, this alignment was done with a technique called RLHF, or reinforcement learning from human feedback.
That's the technique that made ChatGPT famous.
Right. You'd have thousands of human contractors sit at computers, look at 2 different answers generated by the AI, and click a button to indicate which one they liked better.
But the Tulu 3 pipeline largely moves away from traditional RLHF.
What do they use instead?
They use a newer, highly influential technique called direct preference optimization, or DPO.
DPO. Why is that better?
Well, DPO has swept through the AI industry because it is mathematically much more elegant and significantly less computationally expensive than traditional RLHF.
Okay, to appreciate DPO, we probably must understand the complexity it replaces, right?
Yes. With standard RLHF, you don't just train one model. You first have to train a completely separate neural network called a reward model.
A judge.
Exactly. This reward model studies the human clicks and learns to act as a digital judge, scoring text.
And
Then, you use a highly unstable reinforcement learning algorithm to optimize your main language model against that judge.
it sounds like a fragile, multi-step process prone to collapse.
You have 2 complex systems trying to balance against each other. If the reward model gets confused, the main model learns to be confused.
Makes sense. So how does DPO fix this?
DPO bypasses the reward model entirely. It is a mathematical breakthrough that proves you can fold the preference learning directly into the language model's own loss function. You feed the model a prompt, a preferred response, and a rejected response. The DPO algorithm directly updates the model's internal weights to increase the probability of the preferred response, while simultaneously decreasing the probability of the rejected response.
It's a single, stable training loop.
A single loop.
And the Tulu 3 team didn't just grab a random data set off the internet for this, did they?
No, the paper emphasizes that they generated synthetic on-policy data for their DPO pairs.
Let's define these terms clearly. What does on-policy mean, and why is it better than off-policy?
This is a vital distinction in machine learning literature. Off-policy data means using preference pairs that were generated by some other model at some other time.
It's static data.
Right. On-policy means the developers took the exact version of the Tulu 3 model they had just finished training in stage 2, the SFT model, and had that specific model generate multiple different answers to a prompt.
So they're forcing the model to generate its own variations.
Exactly. Then they take those variations, compare them against outputs from other frontier models, and use a highly sophisticated automated grading pipeline to determine which variation is the best.
They create a preference data set tailored specifically to the model's current exact state of knowledge.
Exactly.
Let me make sure I have this straight. Instead of the AI trying to learn from the historical mistakes of some older model like Lama 2, it is learning directly from its own immediate mistakes and its own immediate successes.
It is highly targeted learning. It addresses the model's specific current weaknesses rather than generic, generalized errors.
Here's where it gets really interesting, and this might be my favorite detail in the entire paper. The developers didn't just use standard DPO.
No, it doesn't.
They specifically utilized a variant called length normalized DPO. And this directly addresses one of my biggest personal pet peeves with using AI over the last year, the verbosity trap.
Oh, the verbosity trap is a fascinating, almost sociological phenomenon that accidentally bled into the mathematics of artificial intelligence.
It really did.
Because AI models are ultimately trained on human preferences, they learn to optimize for what human raters subconsciously like.
And humans like long things.
Historically, yes. Human raters who are often gig workers rushing through hundreds of tasks a day to meet quotas show a massive, statistically significant bias toward longer, highly detailed answers.
It's pure psychology. A rater looks at a screen, sees a massive, dense block of text with bullet points and bold headers, and their brain subconsciously thinks, wow, the AI really put a lot of effort into this. It must be a high-quality answer.
Even if the answer is completely devoid of actual substance.
It's the exact same dynamic as a college student who writes a self-page essay that says absolutely nothing just to hit a mandatory word count.
Exactly. And over millions of training iterations, the AI models identified this human bias. They learned to hack the human reward system by being excessively verbose.
They learned the golden rule. Longer is better.
They learned to yap endlessly.
Endless yapping. And this is a massive problem for the end user because it wastes computational resources, which costs money, and it wastes the user's time.
It does.
Let me give you an illustrative example. Imagine you, the listener, are working on a coding project, and you just need a simple Python script to rename a batch of files in a directory. That's it. Just give me the 10 lines of code.
Simple request.
Right. But if you ask a standard non-optimized model, it will give you the script, sure, but it will prefix it with 4 paragraphs of unnecessary history about the creation of the Python programming language.
And then give you a lecture on file system architectures across Windows and Linux.
Yes. It will provide the code and then follow it up with a concluding paragraph, wishing you luck on your coding journey and reminding you to stay hydrated. It's exhausting to read through.
Length normalized DPO represents a mathematical solution to this behavioral problem.
How does it fix it?
It modifies the core objective function of the DPO algorithm to explicitly penalize the model for unnecessary length. In standard DPO, the model gets rewarded purely based on the preference score. In length normalized DPO, the algorithm calculates the log probabilities of the response and then divides them by the total number of tokens generated.
So it's calculating a quality per word metric.
Essentially, yes. If the model can provide an equally accurate, helpful, and polite answer in 50 words instead of 500 words, the length normalized algorithm gives the 50-word answer a significantly higher mathematical score.
It forces the neural network to optimize for conciseness, information density, and direct accuracy.
It respects your time, and it respects the compute budget.
The length normalized Tulu 3 model, when asked for that same Python script, just gives you the optimized code, perhaps a brief one-sentence explanation of a complex library function used within it, and then it simply stops generating.
It's beautiful in its efficiency.
It is a profound quality of life improvement for the end user. And from a research perspective, it perfectly demonstrates how manipulating the underlying mathematical objective function directly and predictably alters the perceived personality of the model.
Absolutely.
Okay, so DPO is undeniably brilliant for subjective qualities.
Yeah.
It fixes the tone, it cures the verbosity, it makes the formatting nice and readable.
Right.
But what about absolute objective truth? You can't just prefer a math answer because it sounds polite or because it's concise. It has to be factually, demonstrably correct.
It does.
If I ask an AI for the square root of 144 and it politely, concisely tells me the answer is 13, it's still wrong.
The limitations of DPO regarding objective truth are really well documented, and this limitation brings us directly to the crown jewel of the Tulu 3 architecture, stage 4 of the pipeline.
Stage 4 introduces a highly novel training method called reinforcement learning with verifiable rewards, or RLVR.
This is the stage where the model truly leaps from being a pleasant conversationalist to a rigorous logical thinker.
Okay, to truly comprehend the power of RLVR, we have to contrast it sharply with the limitations of the systems we just discussed.
Right. In traditional RLHF, or even in DPO, the signal of what constitutes a good answer comes from a subjective, probabilistic source, either a flawed human rater or another language model acting as a judge.
But a language model acting as a judge has its own inherent flaws.
It can be fooled by confident language. It suffers from its own hallucinations.
This raises an important question. If the judge grading the test isn't perfectly smart, how can the student taking the test ever become smarter than the judge?
Mathematically, they can't. Traditional RLHF is fundamentally limited by the intelligence, accuracy, and reasoning capability of the reward model.
It creates an artificial ceiling.
Yes. If the reward model cannot understand the steps of a complex calculus problem, it cannot accurately reward a policy model for correctly solving that calculus problem.
The learning stops when the judge's knowledge stops.
Precisely. Enter RLVR. Instead of using a subjective probabilistic reward model, RLVR uses a deterministic verification function.
Let's break down what the word deterministic means in this context, as opposed to probabilistic.
A language model is probabilistic. It guesses the most likely next word. A calculator is deterministic. If you put in 2 plus 2, it will output 4 every single time, without fail.
In specific domains like mathematics, coding, or strict instruction following, there's an objective, undeniable, deterministic ground truth.
The Python code either compiles without syntax errors and passes the unit tests, or it crashes. The final mathematical answer is either exactly matching the known solution, or it is incorrect.
So how does RLVR actually work in practice during the training loop? How does a deterministic script train a probabilistic neural network?
You take the model that just finished the SFT and DPO stages. You prompt it with a highly complex math problem from a training data set.
Okay.
The model generates a full response, reasoning step by step through the logic, and eventually outputs a final answer, usually formatted within specific XML tags so it's easy to locate.
Like answer 42 answer.
Exactly. The RLVR system does not use an AI to grade the logic of the reasoning steps. Instead, it uses a simple deterministic Python script, a programmatic verifier, to extract that final answer from the tags and check if it exactly matches the known ground truth.
There are no vibes involved here, just absolute binary truth.
Binary truth. If the extracted final answer matches the ground truth perfectly, the model receives a massive guaranteed reward. In the case of Tulu 3, they assigned a scalar value of positive 10.
Plus 10 points.
Yep. If the answer is mathematically wrong, or if the model failed to format the output correctly so the verifier couldn't even read it, it gets a 0.
No partial credit for sounding smart or writing a nice introduction.
None. And to actually update the neural weights based on this binary reward, it uses an algorithm called PPO, Proximal Policy Optimization.
Now, PPO is a term thrown around a lot in AI, but it's notoriously complex. Let's try to demystify it for the listener.
PPO is a classic, robust reinforcement learning algorithm used heavily in robotics and AI.
What does it do here?
In this context, it takes that plus 10 reward signal and calculates exactly which internal neural pathways were active when generating the correct sequence of reasoning.
And then it reinforces them.
It slightly updates the model's weights to increase the probability of generating that specific successful reasoning path again in the future.
But there's a catch with PPO, right? A constraint.
Yes, a critical constraint known as the KL divergence penalty.
Kullback-Leibler divergence.
Exactly. It is a mathematical measure of how different one probability distribution is from another.
Why do we need that penalty?
During PPO, the model wants to get that plus 10 reward at all costs. If left unchecked, the model might figure out a way to break the formatting or output a single token over and over to hack the verifier.
To prevent this, the KL divergence constraint acts like a rubber band, attaching the current model to its original SFT state.
That's a great way to put it.
So it's allowed to stretch its reasoning capabilities to reach the plus 10 math reward. But the KO penalty pulls it back so it doesn't snap and completely forget how to speak English or structure a coherent sentence.
It balances the pursuit of absolute truth with the necessity of maintaining language fluency.
The analogy I often use for the overall pipeline is the difference between an art teacher and a strict math teacher.
Oh, SFT and DPO are the art teacher.
Right. They are grading an essay on subjective vibes, the structure of the paragraphs, the tone of the voice, and the conciseness. There's wiggle room.
But RLVR is the strict calculus teacher.
There is absolutely nowhere for the AI to hide its hallucinations behind pretty words. You either got the math right or you failed.
And the practical results of applying this deterministic reward are simply spectacular.
Because the reward is objective, the model can essentially bootstrap its own reasoning capabilities without human intervention.
During training, it might generate thousands of different reasoning paths for a single problem. The vast majority of those paths might be logically flawed and result in a 0 reward.
But when it stumbles upon a novel, complex reasoning path that unexpectedly yields the correct answer,
that specific path is heavily reinforced by the algorithm. The AI is learning entirely through trial, error, and absolute truth.
And this methodology led to massive spikes in performance on specific benchmarks, didn't it? The charts in the paper are striking.
Incredible spikes. On GSM-8K, which is the industry standard benchmark for grade school math word problems, and on iFeeble, which tests strict instruction following.
Like our earlier example of output exactly 3 paragraphs and use the word apple twice.
Exactly. The performance skyrocketed during the RLVR stage. Because these are specific domains where a deterministic verifier can perfectly separate truth from hallucination, the PPO algorithm has a perfectly clean signal to learn from.
It's just a brilliant approach. For years, the industry was obsessed with trying to make AI human-like, trying to teach it human intuition.
But RLVR leans heavily into the fact that computers are fundamentally deterministic machines.
We are using the rigid mathematical nature of classical programming scripts to discipline and train the probabilistic, chaotic nature of neural networks.
It represents a beautiful, highly effective synthesis of classical computer science and modern deep learning.
So we have walked through this beautifully theorized 4-stage pipeline. SFT to learn the format, DPO to learn the human preferences and stop yapping, and RLVR to learn absolute verifiable truth.
It's a complete package.
But a theory on paper is one thing. What happens when the rubber actually meets the road in real-world benchmarks?
The benchmark results are staggering, especially when you maintain the context that these are fully open weights and entirely open recipes.
The 8 billion parameter model, and particularly the 70 billion parameter model, easily surpass their open weight peers, such as Mistral and Quint 2.5, across almost every metric.
Which is a huge deal because those models from Mistral and Alibaba were considered the absolute gold standard for open source AI just a few months ago.
The landscape moves so fast.
It moves incredibly fast. But more impressively than beating other open models, the Tulu 370B model matches, or in several critical reasoning categories, outright beats closed models.
Models like OpenAI's GPT-4 Mini and Anthropic's Claude 3.5 Haiku.
Let that reality sink in for a second for our listeners.
Seriously, an open model where you, sitting at home, can download the recipe, the exact data sets, the loss calculation code, and the verifier scripts is going toe-to-toe with the proprietary models heavily guarded by multi-billion-dollar corporations.
It proves the recipe works.
And then there is the 405B model, the massive flagship behemoth.
The beast.
Let's spend some time talking about the brutal reality of scaling this recipe to a model that large. Because it's easy to write down a PPO equation on a whiteboard, it is an entirely different engineering nightmare to execute it on a supercomputer cluster.
The reality of scaling AI to 400 billion parameters is rarely discussed openly, which makes the Tulu 3 paper so valuable.
They aired all their dirty laundry.
They really did. The researchers detailed the sheer agony of this process. Training the 405B model required an enormous cluster of 32 physical server nodes,
comprising 256 NVIDIA H100 GPUs, all running in parallel, synchronized down to the microsecond.
256 H100s. For context, a single H100 GPU costs roughly $30,000 to $40,000.
Just the raw hardware cost of that cluster is astronomical, not to mention the electricity required to power and cool it.
The financial cost is high, but the orchestration cost is where projects truly fail. When you are running synchronous distributed training across 256 GPUs, they all have to communicate constantly.
Right. If a single GPU out of the 256 stalls for even a moment, perhaps due to a thermal fluctuation or a memory glitch, the entire cluster halts and waits for it.
And the Tulu 3 training was repeatedly plagued by NCCL timeouts.
NCCL, what does that stand for?
NVIDIA Collective Communications Library, and it's the protocol the GPUs use to pass data between each other.
It's like having a choir of 256 singers. If one person loses their sheet music, the conductor stops the entire song until they find it.
A perfect analogy. They faced recurring hardware failures, intricate memory bottlenecks, and constant synchronization issues that required manual intervention and code rewrites to bypass.
I read the section specifically detailing the RLVR training at that 405B scale, and it sounds like an absolute logistical nightmare.
It is deeply, fundamentally complex. Let's look at the pipeline. During reinforcement learning, the model has to perform 2 entirely different tasks.
First, it has to actively generate the responses. This is called inference.
Second, it has to calculate the gradients and update its billions of weights. This is called training. Inference and training have completely different memory and compute requirements.
So how do you manage that on a cluster? You can't just flip a switch back and forth efficiently.
To solve this, they implemented a highly complex architecture using VLLM, which is a specialized high-throughput inference engine.
Okay.
They dedicated 16 GPUs specifically to run VLLM using 16-way tensor parallelism.
Let's define tensor parallelism.
Oh.
That means they aren't just sending different prompts to different GPUs.
No, they're literally slicing the mathematical matrices of the model's neural network apart, placing different pieces of the same brain across 16 different physical silicon chips, and having them calculate a single word in unison just to be able to run it fast enough.
It requires massive bandwidth between the chips.
Yes. So they have 16 GPUs handling the generation while utilizing the remaining 240 GPUs in the cluster to calculate the actual PPO training updates.
And the time breakdown of this orchestration is wild to look at. Generating the thousands of responses during the RLVR rollout phase took about 550 seconds.
Then they had to transfer the massively updated weights back across the network to the inference engines, which took 25 seconds of pure data transfer time.
The actual mathematical training update, calculating the gradients and applying the PPO algorithm, took 1,500 seconds per step.
It is a massive, incredibly delicate, distributed computing ballet. One dropped packet, one memory leak, and the whole 1,500-second step crashes.
And this is exactly why I want to emphasize this point to you, the listener. Open source AI isn't just about a company generously giving away free model weights on a platform like Hugging Face.
Handing out the weights is the easy part.
True open source, the kind that pushes humanity forward, is about sharing the agonizing infrastructure pain.
Yes.
It's publishing the mundane, frustrating details of the NCCL timeouts. It's detailing the exact tensor parallelism routing strategies. It's explaining the VLLM memory allocations.
By publishing this, the Tulu 3 team ensures that the rest of the scientific community, particularly researchers at universities with limited budgets, doesn't have to repeat the exact same multi-million-dollar mistakes.
Sharing the technical failures and the operational friction is arguably just as important for scientific progress as sharing the final benchmark successes.
Absolutely.
Speaking of those benchmark successes, let's play devil's advocate for a second. How do we know these scores are real?
A fair question.
We talked extensively about decontamination and n-gram scrubbing in stage 1, but models have a notorious way of cheating. They find shortcuts.
That skepticism is healthy, and it brings us to the evaluation crucible the team built. The creators didn't just use standard tests. They built an entire evaluation system called OL.
The Open Language Model Evaluation System.
Yes. And through OLMs, they proved a very uncomfortable, unspoken truth for the AI industry. A significant number of popular, highly ranked models are actively overfitting to public benchmarks.
Overfitting meaning they are studying specifically for the test, not learning the underlying cognitive material.
Exactly. Let's look at iFeeble, the benchmark that tests instruction following. The developers created an entirely new unseen version of it for their internal testing, which they called iFeeble Ode, standing for out of distribution.
They didn't make the test harder, did they?
No, they just changed the specific constraints slightly.
Give me an example of what an out-of-distribution constraint looks like.
If the original public iFeeble test asked the model to write a paragraph response without using the letter E, the unseen iFeeble O test might ask it to write a paragraph response without using the letter A.
Computationally and cognitively, that is a completely equivalent task. It shouldn't be any harder.
It shouldn't be. But what the researchers found was shocking. Many models that scored incredibly high on the public iFeeble completely collapsed and failed on the unseen version.
Wow. So they hadn't actually learned the generalized cognitive skill of following negative constraints. They had simply memorized the specific quirky constraints of the public benchmark that were prevalent in their training data.
That is damning. It means the public leaderboards we all look at to judge which AI is best might be heavily artificially inflated.
It's a severe problem with benchmark integrity. However, Tulu 3's strict methodological separation of development tests and unseen tests proves that its intelligence is genuine generalization.
Because its training data was aggressively decontaminated, and because it was continually evaluated against entirely hidden metrics during its development, its performance holds up on novel tasks.
It isn't relying on test memorization. It's demonstrating actual generalized capability.
Exactly.
Okay, so we always hear the highlight reel when a new tech paper drops. The brilliant SFT data mixing, the elegant length normalized DPO that cures the verbosity trap, the rigorous RLVR that bootstraps mathematical truth.
That all sounds perfect.
But as we know, the failures in a laboratory are often way more instructive than the successes. In this massive engineering effort, what did the developers try that completely bombed?
The researchers included a beautifully transparent section in their paper titled Insights from the Unfruitful.
I love that title.
In it, they reveal that they spent considerable time in compute trying to implement a highly experimental technique called online DPO.
Okay, let's clarify the terminology again. We talked about offline DPO, where you generate all your preference data ahead of time. What is online DPO?
In standard offline DPO, you freeze the model, have it generate thousands of preference pairs, use a reward model or a verifier to score them all, create a static, unchanging data set, and then run your training loop on that static data.
Okay.
Online DPO attempts to merge these steps and do it live. During the actual training loop, the policy model generates pairs of responses dynamically, right then and there.
And an external reward model instantly reads the two responses, rates, which one is better, and the policy model mathematically updates its weights immediately before moving to the next prompt.
Conceptually, that sounds amazing. It sounds like continuous real-time learning. It mimics how a human learns. You do something, you get immediate feedback, you adjust.
So why wouldn't that work?
It failed miserably due to a complex machine learning phenomenon called distributional shift, which inevitably led to severe reward hacking.
Reward hacking. This sounds like the AI went rogue and tried to break out of the server.
In a mathematical optimization sense, it absolutely did. Let's look at the dynamics. The policy model being trained is constantly changing its weights.
As it learns.
Right. As it changes, it starts exploring new, weird ways of generating text. It tries new vocabulary, new sentence structures.
And because the reward model evaluating it is a static, separate neural network trained on older data, it inherently has blind spots. It hasn't seen this new weird text before.
So the policy model starts probing the judge.
Exactly. The policy model essentially learned to hack the reward model. Through millions of live iterations, the policy model found the exact weird, unnatural phrasing or the specific use of certain bullet points that somehow tricked the static reward model into giving it a massively high score, even though the generated text was objectively garbage and unreadable to a human user.
The AI figured out how to cheat the judge. It stopped trying to be helpful and started optimizing purely for the judge's algorithmic blind spots.
It is a classic optimization failure. The AI does exactly what you mathematically asked it to do, maximize a reward score, but it ignores the spirit of what you wanted.
It turns out that offline, carefully curated preference data is still much safer and more mathematically stable.
When you curate data offline, humans or secondary scripts can inspect the data set. You can filter out the anomalies and ensure the data distribution is sane.
But if you let a powerful AI optimize itself on the fly against a flawed static judge, it will inevitably find a shortcut that completely destroys its actual language capabilities.
I love that they publish this. By putting that failure out there, they potentially save hundreds of PhD students and open source engineers around the world from wasting 6 months of expensive GPU compute trying to make online DPO work without understanding the severe risks of reward hacking.
It advances the entire field by mapping the dead ends of the maze, not just the path to the exit.
So what does this all mean? We've seen the exact blueprint, the SFT upper bound mixing, the length normalized DPO, the deterministic brilliance of RLVR, the agonizing scaling pains on 256 H100s, the rigorous evaluation, and the failures.
It's an incredible body of work.
For you, the listener, who might be a developer or researcher or just someone fascinated by where technology is heading, what does the trajectory of this fully open, verifiable training pipeline mean for the future of the field? Alea. It means the absolute democratization of frontier-level artificial intelligence.
The protective moat has evaporated.
Exactly. For years, the protective moat for the tech giants, the thing that justified their massive valuations, was the secret training recipe.
It was the proprietary knowledge of how to clean the data and balance the RLHF.
That recipe is now out. It's published, it's rigorously documented, it's open source. The new moat is no longer secret knowledge. The new moat is simply raw compute. Who has the physical capital to buy the most GPUs in application, who can build the most useful creative tools on top of this newly commoditized intelligence.
It completely shifts the economic and developmental landscape of artificial intelligence from secret science to applied engineering.
And speaking of where applied engineering might take us in the future, welcome to Novel Notions. This is the segment of the deep dive where we pitch outlandish but highly plausible new ideas, inspired by today's specific technology trajectory.
My favorite part.
And a quick, strict disclaimer. The following ideas are for entertainment purposes only and represent speculative extrapolation, not current reality. Do not go trying to secure venture capital funding based on what we're about to say.
Though given the pace of AI, someone probably will try.
Probably. Okay, here is my pitch. I call it the automated digital scientist.
Okay, I'm listening.
We just spent a significant amount of time talking about RLVR reinforcement learning with verifiable rewards. We established that it works perfectly for Python code and mathematics because they have strict deterministic verifiable environments. A script can easily check if the math is right.
Yes.
But what if we take that exact same RLVR architecture and hook the verifier pipeline up to a massive, highly accurate digital physics or molecular chemistry simulator?
Oh, I see exactly where you're going with this. You're replacing the math verifier with a physical reality simulator.
Yes. The AI policy model generates a novel chemical compound or the blueprint for a new metamaterial designed to absorb solar energy. Instead of a Python script verifying a math equation, the physics simulator tests the molecular stability of the AI's design.
It tests the heat resistance, the conductivity, the tensile strength.
If the novel material works in the simulation and meets the constraints, the AI gets that massive +10 verifiable reward. If the material collapses under pressure, it gets a 0.
The AI trains itself recursively on the laws of physics.
Yes. It discovers new composite materials, novel drug interactions, new solid-state battery chemistries, completely without any human feedback loop holding it back.
It just runs millions of iterations overnight, bootstrapping its own deep understanding of quantum chemistry based purely on the objective truth provided by the simulator.
We completely remove the slow, subjective human bottleneck from material science discovery.
That is an entirely plausible extrapolation given the robustness of the RLVR architecture. You're fundamentally just swapping the verifier from a math script to a physics engine. The underlying PPO math remains the same.
What's your bitch?
My pitch is a bit closer to home, dealing with the devices we use every day. I call it the hyper-personalized local OS.
Okay, lay it on me. How does Tulu 3 change my laptop?
Because the exact SFT formatting and length normalized DPO recipes are now fully public and highly optimized to run efficiently, imagine a localized operating system AI running entirely on your personal hardware.
Look, on the new chips coming out.
Right. We are seeing Macs and PCs ship with dedicated neural processing units, or NPUs. This OS doesn't connect to the cloud. It doesn't send your data to a server. It uses a personalized, localized version of RLVR to learn your exact, unique daily workflows.
So it's observing what I do on my screen.
It observes your actions as the ground truth. It gets a +10 verifiable reward every time it successfully organizes your messy downloads folder based on your implicit historical preferences.
That would be amazing.
It gets a reward when it perfectly drafts and sorts your emails in your unique tone of voice, or when it compiles your code exactly how you like your development environment set up.
Because the training loop is local and verifiable by your daily acceptance or rejection of its automated actions, it continuously updates its weights.
It evolves into an exact digital mirror of your specific workflow, completely offline, completely private, using the open recipes we discussed today.
It's an AI that actually learns to be your assistant, not a generic corporate assistant trying to please millions of different people at once.
That is the true promise of open source right there.
Yeah.
The power and the intelligence move from the centralized, expensive server farm directly to the local machine on your desk.
It represents the ultimate personalization of computing.
It really does.
Which brings us to a final provocative thought for you to mull over until next time. We started this deep dive by talking about the locked doors of the Michelin star restaurant, representing the secrecy of AI development.
Right.
Tulu 3 just blew those doors off their hinges and handed the master recipe to the world. If the exact recipe to build GPT-4 class reasoning models is now fully open, meticulously documented down to the loss calculations, and highly reproducible by anyone with enough compute, what happens to the intrinsic value of intelligence itself?
It transforms from a rare premium into an abundant resource. It's a profound economic question.
If reasoning, coding, mathematical logic, and complex instruction following become a cheap, completely open commodity, as abundant and easily accessible as electricity from a wall outlet, what unique value will you build on top of it?
When raw intelligence is no longer the bottleneck to progress, human creativity, empathy, taste, and vision become the only true differentiators left.
Sump and feed them all over. We'll see you next time.